The clock struck 13:47 Universal Time on a Tuesday that shouldn't have been remarkable. But in that single second, something impossible synchronized across 93 million miles of space. The sun exploded. Alaska shattered. Same moment, same instant. Coincidence doesn't stretch that thin. While everyone's been tracking an interstellar visitor called 3I Atlas, a more unsettling pattern has emerged right under our noses. Scientists are quietly terrified, not of what's coming from beyond our solar system, but of what our own star might be doing to the ground beneath our feet. Stay with me through this investigation, because by the end, you'll understand why the next solar storm might matter more than any earthquake forecast. The data suggests we've been watching the wrong sky. If you're as captivated by these cosmic puzzles as I am, consider subscribing to stay connected as we continue tracking these developments. Let me know in the comments where you're watching from, your local time, and whether you think the data we're seeing tells the complete story about what's really happening between our star and our planet. Part 1. The Simultaneous Strike. The clock read 13:47 Universal Time. At that exact second, something impossible happened. Or at least, something that shouldn't be possible according to everything we thought we understood about how our planet works. Imagine a control room filled with monitors. On the left screen, solar observatories capture a monster erupting from the sun's surface. Region 4299, a twisted knot of magnetic field lines, suddenly explodes. An 8.1 M-class flare, powerful enough to light up X-ray detectors across the solar system. Within minutes, a shockwave of plasma billows across space, a full halo coronal mass ejection racing toward Earth at millions of kilometers per hour. The footage is stunning, terrifying even. A star convulsing, throwing tantrums of energy into the void. Now look at the right screen. Seismometers in Alaska. Thousands of instruments measuring the slightest tremor in the ground. At 13:47 Universal Time, the exact same moment the flare detonated, the Earth cracked open. Magnitude 7.0. Not minutes later, not hours later. The same second. Ground motion spikes appear on hundreds of seismograms simultaneously. The rupture tears through rock with the energy of multiple nuclear weapons. Aftershocks begin immediately, over 150 in the following hours, including multiple events above magnitude 5.0. You're looking at synchronized chaos. Solar explosion, terrestrial violence, same timestamp down to the second. Coincidence stretches only so far before it snaps. This isn't the first time observers have noticed temporal proximity between solar events and earthquakes, but it might be the clearest, the most dramatic, the most impossibly precise. Here's why this matters more than you might think. We've always treated the Sun and Earth as separate domains. Solar physics studies the star, seismology studies the planet. They occupy different departments, different journals, different funding streams. The Sun affects our magnetosphere, sure. It creates auroras, disrupts satellites, interferes with radio communications. But crack the ground, move tectonic plates, trigger magnitude 7 earthquakes with split-second timing, that's not in the textbooks. That's not in the hazard models. That challenges foundational assumptions about how energy propagates through space, through the magnetosphere, through hundreds of kilometers of rock. If this synchronization is real, not statistical noise, not cherry-picked data, not confirmation bias, then we're missing something fundamental about Earth's uncoupling. And missing fundamental things about natural hazards gets people killed. It means our infrastructure vulnerability assessments are incomplete. It means regions we think are safe from certain types of disasters might not be. It means the Sun, 93 million miles away, might have a direct line to the most violent geological processes on this planet. So let's ask the uncomfortable question. Could our star be triggering seismic events on Earth, not through slow cosmic ray accumulation or gradual thermal effects, but through real-time electromagnetic coupling? Could there be a mechanism, currently unrecognized or poorly understood, that allows solar storms to reach deep into the crust and nudge critically stressed faults over the edge? The stakes extend beyond scientific curiosity. If such a mechanism exists, we're facing a new category of natural threat. Not just space weather, not just earthquakes, but a hybrid phenomenon that combines both. Imagine trying to forecast seismic hazards without accounting for solar activity. Imagine space weather predictions that ignore geological consequences. We'd be operating half-blind, watching one screen while ignoring the other. This video will walk through the full data chain. We'll examine the solar event in detail, the morphology of the flare and coronal mass ejection, what made this particular eruption unusual. We'll dig into the seismic rupture, the fault geometry, the aftershock sequence, the tectonic context. We'll look for electromagnetic fingerprints, signals in the Earth's natural resonance frequencies that might indicate a global electrical disturbance coinciding with both events. Then we'll explore proposed mechanisms, statistical studies, controversies, and the broader cosmic context that reminds us how much we still don't understand about planetary systems. But let's be clear from the start. We are not claiming certainty, we are investigating. The goal here is to explore the possibility, test the hypothesis against available data, and identify what evidence would be needed to move from speculation to science. This isn't about fear-mongering or apocalyptic predictions. It's about asking whether something genuinely anomalous occurred, and if so, what it means. The sources are transparent. Space weather alerts from NOAA, seismological records from public catalogues, community-monitored electromagnetic data where available. Everything cited, everything checkable. No rumours, no anonymous leaks, no secret documents. Just publicly available observations that happen to align in a way that raises questions. The tone walks a line between science documentary and speculative investigation. We'll follow the evidence where it leads, acknowledge uncertainty when it exists, and remain sceptical of easy answers. But we'll also allow ourselves to wonder, to ask what-if questions, to entertain possibilities that mainstream science might dismiss too quickly. Because sometimes the most important discoveries start as fringe ideas that refuse to go away. Coming up, we'll break down the solar scene, the sunspot region responsible, the sequence of flares, the double explosion captured by coronagraphs, what a full halo coronal mass ejection means for Earth. Then the geology, the Alaska rupture up close, the swarm of aftershocks, the tectonic setting. Then the electrical fingerprint, the claims of Schumann resonance spikes, magnetometer anomalies, the challenge of separating signal from noise. After that, deeper dives into mechanisms, statistics, anomalies, and finally, the big open-ended question haunting this entire investigation. Are we witnessing a new form of Earth-Sun coupling? One that operates on timescales measured in seconds, not centuries? Let's find out. Part 2. The solar scene, sunspot region, flare morphology, and double explosion CME. Solar cycle 25 has been unusually active. Predictions suggested a relatively weak cycle, nothing compared to the monsters of previous decades. Instead, we've seen sustained high sunspot counts, frequent flares and coronal mass ejections that keep space weather forecasters on edge. The Sun, it seems, didn't read the predictions. Region 4299 and 4298 emerged on the solar disk carrying the signatures of danger. High magnetic complexity, twisted field lines wound tight like overwound springs. Multiple sunspots clustered together, dark patches against the bright photosphere where magnetic fields suppress convection and cool the surface. These regions are factories for solar eruptions. Magnetic stress builds as field lines tangle and twist, storing energy until something gives. The sequence began with a teaser. An M1.1 flare erupted first, a moderate event by solar standards. Enough to cause minor radio disruptions, enough to get attention from monitoring stations, but not catastrophic. What matters about this initial flare is timing. It destabilized the magnetic configuration. Think of it as a small earthquake that relieves some stress but leaves the system even more precarious. The main shock was still coming. Hours later, the big one hit, an M8.1 flare pushing toward X-class territory, the designation reserved for the most powerful solar eruptions. X-rays flooded through space, lighting up detectors on satellites. The flare lasted minutes, a brief but violent magnetic reconnection event where tangled field lines snapped and released stored energy in multiple forms. Electromagnetic radiation across the spectrum from radio waves to gamma rays. Accelerated particles, protons and electrons flung into space at relativistic speeds. And plasma, huge amounts of plasma. Coronagraphs captured what happened next. These instruments block the bright solar disk, allowing observation of the faint corona extending millions of kilometers into space. The images showed a double explosion. First, a fast shock front expanding outward, compressing the ambient solar wind, creating a shock wave propagating through interplanetary space. Then the bulk plasma ejection, a massive bubble of magnetized material following behind, carrying billions of tons of solar atmosphere toward Earth. This morphology matters. A full halo coronal mass ejection means the plasma expands nearly symmetrically around the Sun from our viewing angle. That geometry indicates Earth lies somewhere in the path. Not all coronal mass ejections hit us. Most miss entirely, racing off into space at angles that pose no threat to our planet. But full halo events aimed our direction are guaranteed trouble. The shock plus bulk structure creates a 1-2 punch for Earth's magnetosphere. The shock arrives first, travelling faster, compressing the magnetosphere suddenly, creating rapid magnetic field fluctuations. Hours later, the bulk plasma arrives, dense and carrying its own magnetic field. If that field points south, opposite to Earth's north-pointing magnetic field, reconnection occurs on a massive scale. The magnetosphere essentially opens up, allowing solar wind to pour directly toward the poles. That's when geomagnetic storms reach their peak intensity. Let's back up and explain what's actually happening during a solar flare. The Sun's magnetic field is generated by the motion of electrically conducting plasma in the convection zone. In active regions, this field becomes incredibly complex. Imagine rubber bands twisted and stretched and tied in knots. Eventually, the stress exceeds what the structure can contain. Reconnection occurs. Field lines snap, rearrange into simpler configurations, and release the stored magnetic energy as heat, light, and kinetic energy. The process resembles a tightly wound spring suddenly released, or a rubber band stretched to breaking. Magnetic tension converts directly into other energy forms almost instantaneously. Temperatures in the reconnection zone can reach millions of degrees. Particles accelerate to near light speed. Plasma expands outward at hundreds of kilometers per second. For Earth, the typical impacts are well documented. Geomagnetic storms disrupt the magnetosphere, creating fluctuations that induce electrical currents in long conductors like power lines and pipelines. Auroras appear at lower latitudes than usual as energetic particles penetrate deeper into the atmosphere. Satellite operations face increased drag from atmospheric expansion and radiation exposure. Radio communications across certain frequencies become impossible as the ionosphere becomes turbulent. GPS signals degrade. Astronauts face higher radiation doses. These effects are real, measurable, and expected. Space weather forecasting has become a serious operational concern. The Space Weather Prediction Center issued alerts for this event predicting strong geomagnetic storming. That gives it credibility beyond fringe speculation. Official agencies tracking this with government resources, warning power grid operators and satellite controllers. But nowhere in the standard space weather alert does it mention earthquakes. Nowhere in the official forecast models does tectonic activity appear as a potential consequence. The physics connecting solar storms to auroras and satellite disruptions is understood. The physics connecting solar storms to crustal ruptures is not. That's the gap we're exploring. Mainstream seismology would say the idea is implausible. The energy delivered by a geomagnetic storm, even a severe one, is orders of magnitude smaller than the energy released by a magnitude 7 earthquake. Earthquakes are driven by tectonic stress accumulation over decades or centuries. Plate boundaries grind against each other, storing elastic energy in the rock until frictional resistance fails. That's a mechanical process governed by geology, not space weather. Yet here we have synchronization down to the second. The flare explodes, the ground cracks, same moment. If the Sun did explode toward Earth, and Earth responded violently at precisely that instant, what does the geology say? Let's look closer at what happened in Alaska. Part 3. The seismic event up close. Alaska rupture, swarm, and timing. Alaska sits on one of the most tectonically active regions on the planet. The Pacific Plate dives beneath the North American Plate along the Aleutian subduction zone, generating frequent seismicity. Earthquakes here are common. Magnitude 6 events occur regularly. Magnitude 7 events happen every few years. Magnitude 8 or 9 events are rarer but historically documented. This is earthquake country. The ground shakes. People who live here know it. The magnitude 7.0 event struck at 1347 Universal Time. The epicenter location, when plotted on a map, falls within a complex fault network. Determining the exact fault that ruptured requires detailed analysis of seismograms, aftershock distributions and focal mechanisms. Early reports suggested a shallow rupture, meaning the earthquake originated relatively close to the surface, typically more destructive than deeper events, because the energy doesn't dissipate as much through rock before reaching population centres. Seismometers across Alaska and beyond recorded the event. The primary waves, compressional waves travelling fastest through the Earth, arrived first. Then the secondary shear waves, slower but carrying more energy. Finally, surface waves, the ones that cause most of the damage, rippling across the crust like waves on water. The ground motion was violent enough to be felt hundreds of kilometres away. Buildings swayed, roads cracked, landslides triggered in mountainous terrain. What distinguishes this earthquake is the aftershock sequence. Over 150 aftershocks in the hours following the main shock, a remarkably active swarm. Multiple events exceeded magnitude 5.0, large enough to cause additional damage and concern. Aftershock sequences typically follow predictable statistical patterns, the Omori law describing exponential decay in aftershock rates over time. This sequence seemed particularly energetic, suggesting either the main shock transferred stress efficiently to surrounding faults, or the region was already critically stressed across a wide area. Let's put this in context. How common are magnitude 7 earthquakes in this specific region? Alaska averages about 1 magnitude 7 or greater earthquake per year somewhere in the state or offshore. So while large, this event isn't unprecedented. The real question is timing. Earthquakes happen constantly around the world. Approximately 1 magnitude 7 earthquake occurs globally every month on average. So finding a magnitude 7 that coincides with a solar flare isn't impossible by chance alone. Statistical studies examining decades of earthquake catalogues alongside solar activity records consistently find this problem. Earthquakes happen frequently. Solar flares happen frequently. Random coincidences are inevitable. The challenge is distinguishing genuine correlation from noise. Some researchers have attempted this by looking at long-term patterns, correlating geomagnetic indices with seismic rates. Most studies find no significant relationship. A few find weak correlations that might be real or might be statistical artifacts. One complication is defining the time window. If you allow a broad window, say earthquakes within 3 days of a major flare, you increase the chance of finding matches purely by chance. If you narrow the window to hours or minutes, matches become rarer but more suspicious when they occur. This event, with synchronization down to seconds, is about as narrow a window as physically possible. That makes it harder to dismiss as coincidence, but also harder to explain mechanistically. Recent research has explored subtle connections. A 2025 paper suggested that solar heating, transmitted through atmospheric changes, might slightly influence seismic activity globally. The effect proposed was minimal, altering earthquake probability by tiny fractions. Other studies have looked at electromagnetic effects, proposing that induced currents during geomagnetic storms could modulate stress on faults under very specific conditions. These remain minority views within seismology, interesting hypotheses requiring more evidence. The Alaska earthquake by itself proves nothing. It's a data point, one event. To establish a causal link, you'd need a pattern. You'd need multiple instances of similar synchronization. You'd need a plausible physical mechanism. And critically, you'd need to rule out alternative explanations. Maybe this fault was already on the verge of rupturing. Maybe the timing was purely coincidental. Maybe something else triggered it at that exact moment. Something unrelated to the sun. But here's where the story gets more interesting. If this was just a flare and an earthquake, we'd probably shrug and move on. Weird coincidence, nothing more. What elevates this event from curiosity to genuine mystery is the third component, the electrical fingerprint. Reports of electromagnetic anomalies detected at roughly the same time, spikes in extremely low-frequency waves, disturbances in the Earth's natural electromagnetic resonances, data suggesting a global electrical event coinciding with both the solar explosion and the seismic rupture. So yes, the Earth shook. A magnitude 7 earthquake, real and documented. But if we're to treat this as more than coincidence, we need the electric fingerprint. We need evidence that the sun's electrical shock left a trace in Earth's electromagnetic environment. Let's examine what the instruments recorded. Part 4. The electrical fingerprint, Schumann data, magnetometers, and the Tomsk spike. The Earth sits inside a spherical shell of conducting plasma. The ionosphere, beginning around 60 to 80 kilometers altitude, contains free electrons and ions created by solar ultraviolet radiation. Below, the surface is also conductive, especially the oceans. Between these two conducting layers exists a cavity, a spherical resonator for electromagnetic waves. Lightning strikes around the world continuously inject electromagnetic energy into this cavity. The geometry and properties of the system create natural resonance frequencies, known as Schumann resonances after the physicist who predicted them. The fundamental frequency sits around 7.83 Hz, with additional harmonics at roughly 14, 20, 26 Hz, and so on. These frequencies represent standing waves that circle the globe. You can think of the Earth constantly humming at these frequencies, a planetary electromagnetic heartbeat. Monitoring stations equipped with sensitive magnetometers and antennas can detect these resonances. The signals are weak, requiring careful instrumentation and low-noise environments, but they're real, measurable, and have been studied for decades. Under normal conditions, Schumann resonance amplitude varies with lightning activity, which follows diurnal patterns as thunderstorms migrate around the globe with the sun. During severe geomagnetic storms, the ionosphere becomes disturbed. Increased particle precipitation, enhanced conductivity at lower altitudes, compression and expansion of the magnetosphere, all create electromagnetic turbulence. This can show up in Schumann resonance monitoring as increased amplitude, broadband noise, or unusual spectral features. Now here's the contentious part. Some monitoring stations, including one in Tomsk, Russia, reported anomalous signals around the time of the flare and earthquake. Spectrograms allegedly showed a massive spike, broadband energy from near 0 Hz up through 25 Hz or higher. The kind of signal that looks like a global electrical disturbance. The kind of signal that, if real and properly timed, could indicate something extraordinary happened. Treat this claim carefully. Raw spectrograms floating around the internet lack context. What were the local weather conditions? Were there thunderstorms nearby? Was the equipment functioning correctly? Was the data properly calibrated? Did other stations around the world see the same thing at the same time? Without this metadata, a spectacular-looking spike could be anything. Local electromagnetic interference, instrumental artifact, atmospheric lightning, even software glitches. Scientists who study Earth's electromagnetic environment know this field is notoriously difficult. Electromagnetic waves at these frequencies have many sources. Thunderstorms generate continuous background activity. Industrial noise, power lines, electric trains all create interference. Solar-driven ionospheric disturbances are real but complex, varying with time of day, season, solar cycle, and geomagnetic conditions. Isolating a specific signal as definitely solar-induced and definitely connected to seismic activity requires extraordinary care. A convincing detection would need multiple stations globally, all showing similar features at the same time. It would need local weather reports confirming absence of thunderstorms. It would need seismometers confirming absence of other earthquakes that could generate electromagnetic signals. It would need careful timing analysis, showing the electromagnetic anomaly preceded the seismic rupture by seconds or minutes, not following it. Because if the electromagnetic signal came after the earthquake, that's easily explained. Earthquakes themselves generate electromagnetic waves through various mechanisms like piezoelectric effects in crustal rocks. The field exploring electromagnetic phenomena related to earthquakes is called seismoelectromagnetics. Decades of research have attempted to find reliable electromagnetic precursors to earthquakes. The idea is appealing. If rocks under stress generate detectable electromagnetic signals before rupturing, we could potentially predict earthquakes. Unfortunately, despite numerous studies, no robust, reproducible electromagnetic precursor has been established. Signals that look promising in one location fail to appear at others. Signals that correlate with some earthquakes are absent before other similar events. Part of the problem is distinguishing signal from noise. The Earth is electromagnetically noisy. Another problem is the physics. While laboratory experiments show rocks under stress can generate electrical signals through piezoelectric effects, charge separation, or other mechanisms, scaling those effects from hand-sized rock samples to crustal-scale faults is uncertain. And even if pre-earthquake electromagnetic signals exist, that doesn't mean solar activity triggers the earthquake. It could just mean a critically stressed fault was about to rupture anyway. Official statements from agencies like the United States Geological Survey are clear. There is no demonstrated causal link between space weather and earthquakes. The consensus view remains sceptical. Geophysical processes operate on vastly different energy scales than electromagnetic disturbances from solar, storms. But not all researchers dismiss the possibility. Some argue that under extreme conditions, a perfect storm of circumstances, electromagnetic coupling could matter. Imagine a fault already critically stressed, ready to rupture. The energy barrier preventing slip is small. Now imagine a geomagnetic storm inducing unusually strong telluric currents flowing through the crust. If those currents flow through piezoelectric minerals like quartz, common in crustal rocks, they could generate localized stress changes or heat. Maybe, just maybe, that's enough to tip the balance. The proposed effect wouldn't cause an earthquake. It would trigger one that was going to happen anyway, possibly advancing the timing by minutes, hours, or days. The tectonic stress does the real work. The electromagnetic perturbation just gives the final nudge. That's a subtle but important distinction. So we have three components: a solar flare and coronal mass ejection, documented and uncontroversial; an earthquake, documented and uncontroversial; and claimed electromagnetic anomalies, documented but highly controversial. The combination is intriguing, suggestive, but far from proof. This could be noise, random instrumentation artifacts, coincidental thunderstorms, or it could be the fingerprint of a global electric shock propagating from space through the magnetosphere to the ground, coinciding with tectonic rupture. The difference matters immensely. One implies business as usual, interesting coincidence, move along. The other implies we're missing fundamental physics about how planets interact with their stars, about energy transfer mechanisms operating on timescales we didn't think possible, about hazard categories we haven't properly recognized. From the sun's blast to Earth's tremor, a clean causal chain still eludes us. But we know enough to frame what we don't know. We know what data would be needed to test this properly. We know the questions to ask. And asking the right questions is often the first step toward discovering uncomfortable truths. Part 5. Short verdict so far. What we can say and what remains unknown. Let's pause and take inventory. What do we actually know? What can we say with confidence? And where does confidence break down into speculation? Three components are real, documented, and not seriously disputed. First, a powerful solar flare occurred, M8.1 class, followed by a full halo coronal mass ejection directed toward Earth. Space weather monitoring satellites recorded the event. Official agencies issued alerts. This isn't conspiracy theory territory. This is government space weather infrastructure doing its job, tracking a significant solar storm. Second, a magnitude 7.0 earthquake struck Alaska at 1347 Universal Time. Seismometers across multiple networks recorded it. Aftershock sequences followed predictable patterns. Damage occurred. People felt it. This earthquake is catalogued in official databases. Its reality is not in question. Third, reports exist of electromagnetic anomalies detected around the same time frame. Schumann resonance monitors, community magnetometer networks, and other instrumentation allegedly recorded unusual signals. This component is more controversial because the data quality varies, metadata is often missing, and distinguishing genuine signals from artifacts is difficult. But the reports exist. People claiming to have detected something. Whether those detections represent real geophysical phenomena or instrumental noise remains unresolved. Now, what can we not confidently claim? We cannot claim a proven deterministic mechanism linking solar flares to earthquakes. The physics required for such a mechanism remains speculative, poorly understood, and unsupported by the bulk of peer-reviewed literature. We cannot claim this event definitively proves causation. One event, no matter how striking, doesn't establish a pattern or validate a hypothesis. The prevailing scientific consensus remains skeptical, often dismissive. Mainstream seismology treats the crust and mantle as essentially isolated from space weather effects, beyond negligible thermal variations and cosmic ray influences. Mainstream space weather science focuses on magnetospheric, ionospheric, and technological impacts. The intersection, solar activity influencing tectonic processes, exists in a marginal zone where few researchers work and funding is scarce. So where does that leave us? With an event intriguing and unusual enough to merit serious scientific follow-up, but not yet evidence of a paradigm shift. Think of it as an anomaly worth investigating, not a revolution already validated. Anomalies drive science forward when they're taken seriously, studied rigorously, and either explained within existing frameworks or used to expand those frameworks. What would convincing proof require? A checklist helps clarify thinking. First, global time synchronized instrumentation, magnetometers, extremely low-frequency sensors, seismometers, ionospheric monitors, all recording continuously with accurate timestamps. Second, public data archives with full metadata, calibration information, local weather conditions, instrumental specifications, everything needed to verify and replicate analyses. Third, cross-disciplinary collaboration. Space weather physicists working with seismologists, geophysicists, electromagnetic specialists, pooling expertise. Fourth, multiple documented instances. One coincidence is interesting. 3 similar coincidences raise eyebrows. 10 become a pattern. 20 demand explanation. Fifth, controlled studies ruling out alternative explanations. Statistical tests showing correlation exceeds chance. Physical models predicting where and when effects should appear. Then observations confirming those predictions. Sixth, peer-reviewed publication and independent replication. Claims published in reputable journals, analysed by skeptical experts, replicated by independent teams. None of those conditions are fully met yet. We have pieces. We have intriguing data fragments, suggestive correlations, plausible but unproven mechanisms. What we lack is the comprehensive, rigorous, multi-institution research program needed to resolve the question definitively. Why does this matter beyond academic curiosity? Because if even a fraction of the proposed coupling is real, it fundamentally changes planetary risk assessment. Natural hazard models currently treat solar storms and earthquakes as independent threats. Space weather forecasting considers technological infrastructure, not geological stability. Seismic hazard forecasting considers tectonic stress, not space weather. If they're coupled, even weakly, we're modelling risk incorrectly. Regions thought safe from certain hazard combinations might not be. Critical infrastructure might face correlated failures, space weather and seismic damage striking simultaneously when we expect them separated. Early warning systems might need integration across disciplines currently operating independently. There's also a responsibility aspect. These kinds of claims, solar storms triggering earthquakes, resonate powerfully with public fears. They mix cosmic scale with immediate personal danger. They tap into anxieties about our vulnerability, our inability to control or predict nature, our dependence on systems fragile in ways we barely understand. That makes it fertile ground for misinformation, for fear-mongering, for apocalyptic narratives detached from evidence. We must treat claims like these with curiosity, absolutely, but also with rigour. Avoid clickbait panic, demand transparency and data, distinguish between we don't know and we know it's false. Maintain epistemic humility. Science progresses by investigating anomalies, not by dismissing them reflexively, but also not by accepting them uncritically. The scientific method exists precisely for situations like this. When observations seem to contradict established understanding, you don't immediately tear down the old framework. You examine the observations carefully, test for errors, propose mechanisms, gather more data, refine hypotheses. Sometimes the anomaly disappears under scrutiny, an artifact or misunderstanding. Sometimes it persists, forcing revision of existing models. The process itself, careful investigation regardless of outcome, is where value lies. We're now ready to dive deeper. To explore the mechanisms proposed for electromagnetic coupling, the physical processes that could, hypothetically, allow solar storms to influence seismic activity. Then we'll examine statistical evidence, decades of attempted correlations, the pitfalls and challenges of proving causation in complex Earth systems. We'll look at anomalies, odd features of this specific event that make it stand out. And finally, we'll broaden the view, placing this mystery in a wider, cosmic context that reminds us how much remains unknown about planetary systems, stellar influences, and the universe we inhabit. The investigation continues. Part 6. Electromagnetic coupling. Physically. Telluric currents. ionospheric pumping, piezoelectric effects. The mechanism sounds almost absurdly simple when you first hear it. A coronal mass ejection slams into Earth's magnetosphere. The magnetosphere compresses, magnetic field lines reconnect, electric fields appear, currents flow through the ionosphere and down into the ground. Those currents interact with minerals and crustal rocks. Stress patterns shift. A fault on the edge of failure slips. Earthquake. Simple to describe? Yes, but the devil lives in the details, and those details are where certainty collapses into speculation. Let's walk through the physics step by step, using language accessible to anyone who remembers high school science, because understanding the mechanism matters more than accepting it blindly. When a coronal mass ejection arrives at Earth, it doesn't hit the surface. It hits the magnetosphere first, that invisible magnetic bubble extending tens of thousands of kilometers into space. The impact compresses the magnetosphere on the day side, sometimes pushing it inward by thousands of kilometers. On the night side, magnetic field lines stretch outward, creating a magnetotail. The whole system convulses, field lines twisting, breaking, reconnecting in violent bursts. This happens fast. Within minutes, sometimes seconds, the magnetic field strength at Earth's surface can change significantly. Now here's where basic physics becomes important. Faraday's law of electromagnetic induction states that a changing magnetic field induces an electric field. It's the same principle behind electric generators, transformers, and wireless charging. Change the magnetic field through a loop of wire and current flows. Earth has conductors. The ionosphere, filled with free electrons and ions, conducts electricity quite well. The oceans, salty and conductive, form another layer. Even solid ground contains minerals with varying conductivity. When Earth's magnetic field changes rapidly during a geomagnetic storm, electric fields appear. These fields drive currents through any available conducting path. In the ionosphere, these are called ionospheric currents. In the ground, they're called telluric currents. Picture waving a giant bar magnet around a coil of wire. The faster you wave it, the stronger the induced current. A coronal mass ejection acts like that, except the magnet is planetary scale and the coil is Earth itself. The currents induced can be substantial, strong enough to damage power grids, corrode pipelines, interfere with communication cables. We've documented these effects extensively. What remains uncertain is whether these currents reach deep enough and carry sufficient energy to influence fault mechanics. Here's where piezoelectric effects enter the conversation. Quartz, one of the most common minerals in Earth's crust, exhibits piezoelectricity. Apply mechanical stress to quartz and it generates electrical charge. Apply electrical charge and it deforms mechanically. The effect is small but measurable. Laboratory experiments demonstrate it clearly. Scaling from lab samples to crustal volumes involves enormous uncertainties, but the physics is real. Imagine telluric currents flowing through rock containing abundant quartz. Those currents could generate mechanical stresses via piezoelectric coupling. Alternatively, they could heat the rock slightly through resistive heating, changing fluid pressure in pore spaces, altering friction along fault surfaces. Another possibility involves charge redistribution. Faults are complex zones with fluids, fractured rock, and mineral interfaces. Electrical currents might change the electrical state of fault zones in ways that modify friction or cohesion. A 2025 paper explored a different angle. It suggested that solar heating transmitted through atmospheric changes might influence seismic activity globally. The effect proposed was tiny, altering earthquake probabilities by minute fractions. That study remains controversial, but represents a growing willingness among some researchers to consider solar influences beyond traditional space weather effects. Contrast that with the skeptical majority. Long-term statistical analyses spanning decades find no clear link between solar activity and earthquakes. Energy budget calculations suggest the problem is insurmountable. A magnitude 7 earthquake releases approximately 2 quadrillion joules of energy. A severe geomagnetic storm delivers perhaps a billionth of that to Earth's surface through electromagnetic coupling. The numbers don't match. Orders of magnitude separate them. Let's do rough back-of-envelope math. Typical geomagnetic storms induce electric fields at Earth's surface on the order of 1 to 10 volts per kilometre. Strong storms might reach a few hundred volts per kilometre in extreme cases. Compare that to the gigapascals of stress required to rupture rock along a fault plane. The energy density mismatch is enormous. Many researchers conclude on this basis alone that electromagnetic triggering is physically implausible. But here's the counter-argument, the threshold hypothesis. What if electromagnetic coupling doesn't need to provide the earthquake's energy? What if it only needs to provide a tiny nudge to a fault already critically stressed? Think of a boulder balanced on a hilltop. It contains gravitational potential energy. A small push, trivial compared to the boulder's weight, sends it tumbling. The push didn't create the energy. It released energy already stored. Faults work similarly. Tectonic stress accumulates over years, decades, centuries. Eventually stress exceeds frictional resistance. The fault slips. But near the critical point, the system is exquisitely sensitive. Small perturbations might matter. Tidal forces from the moon and sun, which are far weaker than tectonic stresses, have been statistically linked to earthquake triggering in some studies. If tides can matter, maybe electromagnetic effects can too under the right circumstances. Those circumstances would require alignment of multiple factors. A massive coronal mass ejection, delivering an unusually strong geomagnetic disturbance. A fault already loaded to near critical stress. Favourable fault geometry, perhaps oriented to maximise coupling with induced currents. High conductivity rock surrounding the fault. Abundant piezoelectric minerals. It's a long list. Each requirement makes the scenario rarer. But rare doesn't mean impossible. We don't know the conductivity structure of crustal rock around specific faults. We don't have detailed maps of mineral distributions. We don't understand fault zone internal structure well enough to predict how electromagnetic disturbances would propagate through them. Timing synchronization requires data log to sub-second precision, which is rare. Most critically, we have almost no repeatable peer-reviewed case studies demonstrating the effect. This hypothesis occupies uncomfortable territory, not science fiction, because the physics involved are real and understood, but borderline fringe because evidence remains sparse and ambiguous. It's bold, intriguing, and deserving of serious investigation, but it must be investigated with humility, acknowledging that extraordinary claims require extraordinary evidence. One event, no matter how coincidental, doesn't validate the mechanism. We need patterns, replication, controlled studies, and theoretical models that make testable predictions. Even if the physics could work under perfect conditions, that doesn't mean it works routinely or detectably. The universe is full of physically possible phenomena that occur too rarely or weakly to matter practically. The question becomes, is electromagnetic earthquake triggering one of those rare edge cases worth worrying about? Or is it a phantom correlation amplified by pattern-seeking minds? To answer that, we need to look at what decades of statistical studies actually show. Do the numbers support a link, or do they demolish it? Part 7. Statistical evidence and pitfalls, correlations, lags, and selection bias. Statistics should settle this. We have earthquake catalogues going back decades, sometimes centuries. We have solar activity records, sunspot counts, flare classifications, geomagnetic indices, all meticulously logged. If solar storms trigger earthquakes, the pattern should emerge from the data. Correlate solar activity with seismic rates. Control for confounding variables. Test statistical significance. Science has the tools. So what do the studies show? The answer is frustratingly messy. Some studies report weak correlations. Others find nothing. A few claim strong relationships that later studies fail to replicate. The field is littered with contradictory results, methodological disputes, and accusations of cherry-picking. Let's unpack why. A 2025 study investigated geomagnetic activity and earthquake occurrences, attempting to quantify any relationship. The authors examined decades of data, comparing geomagnetic storm timing with earthquake catalogues. They found some weak correlations suggesting a slight uptick in seismic activity days to weeks after strong geomagnetic events. The effect was small, statistically marginal, and inconsistent across different regions and magnitude thresholds. Other research reached opposite conclusions. The 2013 analysis, covering a full solar cycle, found no clear evidence linking large flares to earthquakes. The study looked at hundreds of major flares and thousands of significant earthquakes. If a robust connection existed, it should have appeared. It didn't. The earthquakes seemed to occur randomly with respect to solar activity, no more frequently after flares than before them. Why the discrepancy? Methodology matters enormously. Selection bias is a constant threat. researchers sometimes focus on interesting events, large earthquakes coinciding with large flares, while ignoring the countless cases where flares occurred without earthquakes, or earthquakes occurred without flares. This creates an illusion of correlation. Your brain remembers the matches, forgets the mismatches, and concludes a pattern exists. The multiple comparison problem compounds this. With hundreds of flares every solar cycle, and thousands of earthquakes globally, random coincidences are inevitable. Flip a coin enough times, you'll eventually get 10 heads in a row. Doesn't mean the coin is biased. Similarly, finding a few dramatic flare plus quake coincidences across decades of data doesn't prove causation. It might just be chance. Definition issues plague these studies. What counts as a solar event? M-class flares only? Include X-class? What about coronal mass ejections that aren't accompanied by strong flares? Should you track geomagnetic indices like the KP index instead? Each choice changes the analysis. Similarly, what earthquake magnitude threshold should you use? Magnitude 5 and above? Magnitude 6? Global catalogue or specific tectonic regions? Different thresholds yield different results. Time window assumptions introduce another variable. If you claim solar storms trigger earthquakes, how long after the storm should you look? Within 24 hours, 72 hours, a week, a month? Different studies use different windows. Wider windows increase the chance of finding coincidental matches. Narrower windows might miss real effects if there's a delayed triggering mechanism. But without a physical model predicting the delay, the choice becomes arbitrary. Imagine overlaying two time series. One shows sunspot counts, fluctuating over the 11-year solar cycle. The other shows earthquake frequency, also fluctuating but for different reasons. Tectonic loading cycles, regional stress patterns, aftershock sequences. Visual overlap can be misleading. Your eye picks out moments where both curves spike simultaneously and thinks, aha, correlation. But statistical tests might reveal those overlaps are no more frequent than random chance would predict. Overlapping waveforms doesn't prove one drives the other. Correlation doesn't imply causation, as every statistics student learns. Two variables can correlate because one causes the other, because a third variable causes both, or because of pure coincidence. Distinguishing these requires careful experimental design, control groups, and mechanistic understanding. With solar seismic correlations, we lack controlled experiments. We can't turn the sun on and off. We observe what nature provides and try to extract signal from noise. Recent approaches have become more sophisticated. Some researchers now use spectral analysis, looking for periodic signals in earthquake occurrence rates that match known solar periodicities. The sun rotates roughly every 27 days. Solar wind streams from coronal holes can create 9-day or 13.5-day periodicities. If earthquakes modulate with those cycles, that would suggest a connection. A 2025 paper summarized such patterns, claiming to find weak but statistically significant periodicities in global seismic catalogues matching solar rotation. The authors suggested this might reflect genuine, if subtle, solar influence. Critics counter that with enough data and enough periodicities to test, spurious correlations are inevitable. Earthquakes also respond to earth tides, which have their own periodicities. Seasonal variations exist due to groundwater changes, atmospheric pressure, ice loading. Disentangling solar effects from these other cycles is extraordinarily difficult. Even if you find a weak periodic signal, it doesn't prove causation. Maybe it's coincidental, maybe some other factor, something we haven't considered, causes both solar activity and seismic activity to vary together. Perhaps cosmic ray flux, modulated by the solar cycle, influences atmospheric processes, which influence crustal stress via barometric loading. That's speculative, but it illustrates how indirect pathways could create correlations without direct solar tectonic coupling. The peer-reviewed consensus remains skeptical. Most seismologists, when surveyed, expressed doubt about solar triggering. Most solar physicists focus on magnetospheric and ionospheric effects, not crustal dynamics. The idea lives in a marginal zone between disciplines, advocated by a minority of researchers who believe the question deserves more attention. But the door isn't closed. Some intriguing instances remain unexplained and worthy of further investigation. Individual case studies, like our Alaska event, where timing is suspiciously precise, clusters of earthquakes following major geomagnetic storms that seem statistically unusual, anomalous electromagnetic signals preceding or accompanying seismic events. These don't prove the hypothesis, but they prevent outright dismissal. Here's the statistical realpolitik. If you manipulate your criteria enough, stretch time windows, cherry-pick magnitude thresholds, select specific geographic regions, you can manufacture a correlation. That doesn't satisfy scientific rigor. Real correlation requires pre-registered hypotheses, clearly defined criteria applied consistently, independent replication, and plausible physical mechanisms. Without those safeguards, you're just finding patterns in noise, seeing faces in clouds, connecting dots that don't form a picture. Yet dismissing the question entirely risks missing something real. History is full of dismissed ideas later proven correct. Continental drift, meteorite impacts causing extinctions, prions as infectious agents, all faced initial skepticism. The key is maintaining appropriate skepticism while remaining open to evidence. Demand high standards, insist on transparency, but don't close the book prematurely just because current data is ambiguous. So statistics haven't settled it. The data's noisy, the method's disputed, the results contradictory. That doesn't mean nothing's there. It means if something's there, it's subtle, rare, or contingent on conditions we haven't identified. Which brings us to the anomalies, the weird edges of this story that make it more than just a statistical debate. Let's examine what makes certain events, like our Alaska case, stand out from the background noise. Part 8. The anomalies and the odd edges. Double explosion, precursor silence, and geometry claims. Some events refuse to fit neatly into statistical summaries. They possess features that make them memorable, suspicious, or just plain weird. Our Alaska event carries several such features. The double explosion coronal mass ejection morphology, the claimed precursor silence before the earthquake, and most speculatively geometric relationships to ancient sites. Let's examine each anomaly, evaluate its credibility, and consider what, if anything, it tells us. The double explosion coronal mass ejection stands out immediately. Most coronal mass ejections show a single bulk plasma cloud expanding into space. This one showed two distinct components. First, a fast shock front racing ahead, compressing the ambient solar wind. Then, hours later, the bulk plasma following behind, dense and carrying strong magnetic fields. Coronagraph imagery captured both clearly. Could this morphology deliver a more potent disturbance to Earth's magnetosphere than typical coronal mass ejections? Possibly. The shock front arrives first, compressing the magnetosphere suddenly, creating rapid magnetic field fluctuations. Before the system recovers, the bulk plasma arrives, potentially driving sustained geomagnetic activity. This 1-2 punch might create conditions more favourable for induced currents, more intense ionospheric disturbances, greater electromagnetic stress on any coupled systems. But is it unique? No. Double or multiple coronal mass ejection events occur regularly, especially during active solar periods. Sometimes two eruptions from the same active region occur hours apart. Sometimes successive coronal mass ejections interact in interplanetary space, the faster one overtaking the slower, creating complex shock structures. Solar physicists study these interactions routinely. They're interesting but not extraordinarily rare. Alternative explanations exist. The double structure could reflect coronal mass ejection interaction from two separate eruptions. It could represent complex magnetic topology in the source region, with multiple flux ropes ejecting sequentially. It might even be an observational artifact, projection effects from viewing angle making a single structure appear double. Without detailed magneto-hydrodynamic modelling of the specific event, we can't definitively say this coronal mass ejection was exceptional in ways that matter for earthquake triggering. Now consider the precursor silence claim. 2 weeks before the magnitude 7 earthquake, a magnitude 6 event struck the same general region. Aftershock activity following that magnitude 6 quake was reportedly anomalously low. Some interpret this as stress locked in the crust, waiting for a trigger to release it. The argument goes, normal aftershock sequences indicate stress redistribution and gradual relaxation. Suppressed aftershocks might indicate stress accumulation continuing, the system approaching critical instability. Seismologists know that earthquake sequences vary enormously. Some main shocks trigger robust aftershock swarms, hundreds or thousands of events. Others produce few aftershocks. The reasons involve fault geometry, stress heterogeneity, fluid pressure, rock properties, and factors we don't fully understand. Quiet periods before large earthquakes do occur, but they're not rare or diagnostic. Attempting to predict earthquakes based on seismicity patterns has failed repeatedly. The crust is too complex, the signal's too ambiguous. The precursor silence is anecdotal, not a robust signal. It might reflect normal variability. It might result from aftershock detection thresholds, with small events occurring but not recorded. It might indicate a seismic slip, stress relieved through slow fault creep rather than detectable earthquakes. Without detailed strain measurements and subsurface monitoring, interpreting seismic quietness is guesswork. Then there's the geometry claim, by far the most speculative. The suggestion is that Alaska's epicenter lies at a specific geometric relationship to ancient megalithic sites like Giza, Nazca, and Angkor Wat. The implication is that Earth possesses vibrational nodes, points of special geophysical significance, and ancient cultures somehow mapped them, encoding that knowledge in monument placement. Let's be clear, this is fringe territory, bordering on pseudoscience. Testing such claims rigorously is nearly impossible because pattern seeking on a sphere is trivially easy. Earth's surface contains thousands of archaeological sites. Pick any three, draw great circles connecting them, and those circles will pass through countless other locations. If you search long enough, you'll find geometric relationships between any set of points you choose. There are tens of thousands of potential location triplets. The probability that some subset exhibits interesting geometry approaches certainty. It's like finding words in alphabet soup. Stir long enough and patterns emerge. That doesn't mean the soup is trying to communicate. It means human brains excel at finding patterns, even in random data. If you connect three major cities randomly, say New York, Tokyo, and Cairo, the arcs between them pass through many other regions. Someone could declare those regions special, based purely on the geometric coincidence. Add enough criteria, ancient sites, earthquake epicenters, volcanic vents, magnetic anomalies, and you can construct elaborate theories. But without independent evidence, these remain exercises in pareidolia, seeing meaningful patterns where none exist. Could there be anything to vibrational nodes? Earth does have natural resonance modes, free oscillations excited by large earthquakes. These are global phenomena, mathematically describable and well studied. But they don't create fixed points on the surface with special properties. They're standing waves in the entire planet, not localized nodes determining where earthquakes occur. Evaluate each anomaly honestly. The double explosion coronal mass ejection is real but not unique. It's unusual, worth noting, but doesn't scream super trigger louder than other major coronal mass ejections. The precursor silence is real in the sense that aftershock activity varied, but it's not rare or predictive. Many earthquakes show similar patterns without subsequent major events. The geometry claim is intriguing if you're inclined toward mystery, but scientifically it's untestable and likely coincidental. Why do these anomalies matter? They make the story compelling. They provide narrative hooks, elements that capture imagination and suggest hidden connections. The double explosion sounds dramatic. The quiet before the storm evokes suspense. Ancient geometric patterns tap into our fascination with lost knowledge and cosmic design. These elements blend science with myth, data with speculation, creating fertile ground for both discovery and misinformation. This is where responsible communication becomes critical. Presenting anomalies is fine, even necessary. Science progresses by investigating outliers. But we must label speculation clearly. State what's known, what's guessed, and what's fantasy. The double explosion happened. Whether it mattered is speculation. The precursor quiet happened. Whether it predicted anything is speculation. The geometry exists if you look for it. Whether it means anything is almost certainly fantasy. These odd edges blur boundaries between scientific investigation and pattern-seeking storytelling. That's not inherently bad. Human curiosity thrives on mystery. But crossing that line without acknowledging it risks spreading misinformation, encouraging unfounded fears, or building belief systems on statistical coincidences. We can explore the weird edges while maintaining intellectual honesty. That's the balance this investigation attempts to strike. Given all these uncertainties and anomalies, what would a smoking gun dataset actually look like? If we're serious about testing whether solar storms can trigger earthquakes, what data do we need and how should it be collected? Let's build a forensic checklist, a roadmap for turning speculation into science. Part 9. Hidden datasets and forensic checklist. What we really need. Testing a hypothesis properly requires the right tools, the right data, and the right protocols. If we're claiming solar storms might trigger earthquakes through electromagnetic coupling, we need to catch the phenomenon in action, with instrumentation comprehensive enough to rule out alternative explanations. That's a tall order, but let's break down exactly what would be required. First, high-rate ground magnetometer data in and around seismic regions. Fluxgate magnetometers and search coil sensors capable of recording magnetic field variations at sub-second time resolution. These instruments would need to operate continuously, logging data with accurate timestamps synchronized to universal time via GPS or atomic clocks. Multiple stations arranged in arrays would allow triangulation of electromagnetic disturbances, distinguishing local anomalies from regional or global phenomena. Second, broadband extremely low frequency and Schumann resonance monitoring globally distributed. These sensors detect electromagnetic waves from near 0 Hz up through at least 30 Hz, covering the Schumann resonance fundamental and harmonics. Strict calibration is essential. Each sensor must have known frequency response, documented noise floors, and environmental monitoring to identify local interference sources. Without calibration metadata, spectacular-looking signals could be anything from thunderstorms to malfunctioning equipment. Third, broadband seismometers and strain meters, ideally installed in boreholes to reduce surface noise. These would record not just the earthquake itself, but any subtle changes in ground strain or microseismicity preceding the rupture. Strain meters are particularly useful because they can detect aseismic deformation, slow fault creep that doesn't produce detectable earthquakes but indicates stress, redistribution. Borehole installations provide better coupling to bedrock and reduce sensitivity to surface weather effects. Fourth, ionospheric measurements. Global Navigation Satellite System. Total electron content maps derived from GPS and other satellite networks show ionospheric density variations. Ionosonde data provides altitude profiles of electron density. These measurements detect ionospheric disturbances driven by geomagnetic storms. If electromagnetic coupling to the ground matters, the ionosphere should show correlated disturbances. Combining ionospheric data with ground measurements would constrain energy flow from space to Earth's surface. Fifth, satellite data capturing the solar event itself. GOES satellites monitor solar X-rays and energetic particles in real time. SOHO and LASCO coronagraphs image coronal mass ejections. Solar wind monitors at the L1 Lagrange point measure plasma density, velocity, temperature, and magnetic field. Together, these provide complete characterization of the solar storm from eruption through interplanetary propagation to Earth impact. Knowing exactly what hit us and when is essential for correlating effects. Sixth, environmental and atmospheric monitoring. Weather station data showing thunderstorm activity, barometric pressure changes, precipitation. Lightning detection networks recording electromagnetic transients from atmospheric discharges. These rule out false positives. If your extremely low-frequency sensor shows a spike during a local thunderstorm, that's not a solar-driven signal. Comprehensive environmental monitoring separates genuine geomagnetic effects from atmospheric noise. Metadata is crucial throughout. Accurate universal time timestamps synchronized across all instruments. Clock drift monitoring and correction. Calibration records documenting sensor response, installation details, maintenance history. Publicly accessible raw data archives, not just processed summaries or cherry-picked examples. Error bars and uncertainty estimates. Without this metadata, data is nearly useless for rigorous analysis. Now let's propose a 6-point forensic pass-fail rubric for evaluating any future claimed solar-triggered earthquake. First, time synchronization check. The electromagnetic anomaly and seismic event must be temporally correlated within seconds to minutes, with independently verified timestamps. If timing is uncertain by hours or days, causation is impossible to establish. Second, multi-station electromagnetic concurrence. Multiple independent monitoring stations, preferably globally distributed, must record similar anomalous signals simultaneously. If only one station sees something, suspect instrumental artifact or local interference. Global coherence is the signature of a genuine geomagnetic disturbance. Third, absence of local atmospheric disturbances. Weather records must confirm no thunderstorms, no unusual lightning activity, no electromagnetic interference from human sources at the critical times. This requirement rules out the most common false positives. Fourth, temporal proximity with correct ordering. The electromagnetic anomaly must precede or coincide with the seismic rupture, not follow it. If electromagnetic signals appear after the earthquake, that's easily explained by the earthquake itself generating electromagnetic noise through various mechanisms. Precursor signals are what would support triggering. Fifth, geophysical mechanism plausibility. The proposed coupling mechanism must be physically reasonable given known fault geometry, rock conductivity, mineral composition, and tectonic stress state. Not every fault should be equally susceptible. The mechanism should predict which conditions favour coupling and which don't, allowing testable predictions. Sixth, peer-reviewed reproducibility. The analysis must be published in reputable journals, scrutinised by experts, and ideally replicated by independent researchers using the same methods on different events. One-off claims without independent verification prove nothing. Science requires reproducibility. Only if a dataset passes all 6 criteria should a claim of solar-triggered earthquake be taken seriously. Passing 2 or 3 is interesting but insufficient. All 6 represent the minimum standard for extraordinary claims. Why are such datasets rare? Multiple reasons. Funding for cross-disciplinary research combining space weather and seismology is limited. These fields exist in separate communities with different priorities. Instrumentation is expensive. Installing and maintaining global networks of synchronized sensors requires sustained investment. Data siloing is common. Different agencies collect different datasets, often with incompatible formats or restricted access. Seismo-electromagnetics has historically been viewed as fringe, which creates a vicious cycle. Because it's fringe, funding is scarce. Because funding is scarce, high-quality datasets don't get collected. Because datasets don't exist, the field can't mature or gain credibility. Breaking this cycle requires institutional commitment to open questions and willingness to fund investigations even when outcomes are uncertain. But the value extends beyond proving or disproving solar triggering. Building this data infrastructure would improve our understanding of space weather hazards generally. It would enhance earthquake early warning systems by providing additional sensor networks. It would advance fundamental geophysics, mapping crustal conductivity and electromagnetic properties. Even if solar triggering proves negligible, the research yields benefits. Encouraging viewer involvement matters too. Open data movements, citizen science, distributed monitoring networks all democratize scientific investigation. Amateur radio operators, for example, have contributed valuable ionospheric data for decades. Individuals with basic electronic skills can build extremely low-frequency receivers and magnetometers, contributing to community networks. Public pressure on institutions to release archived data accelerates progress. Science benefits from transparency and participation. Beyond data and mechanisms, there's a larger story unfolding about how we handle uncertainty, how media and public discourse amplify fear or hope, how the boundary between science and speculation becomes contested territory. Understanding the sociology of this debate matters as much as understanding the physics. Let's examine that landscape. Part 10. Controversies Sociology and how the science versus alternative media split amplifies fear. Dramatic coincidences are catnip for content creators. A massive solar explosion and a magnitude 7 earthquake at the same instant. That's the stuff of viral videos, social media threads, and late-night documentaries. Add claims of electromagnetic anomalies and ancient geometric patterns, and you have a narrative that writes itself. The question is whether that narrative serves truth or exploits fear. Confirmation bias operates powerfully here. Once someone accepts the premise that solar storms trigger earthquakes, every subsequent coincidence reinforces belief. They notice every large earthquake following a solar flare. They ignore the countless solar flares producing no earthquakes, and the countless earthquakes occurring during solar quiet periods. The brain selectively attends to confirming evidence, filtering out contradictions. Over time, weak correlations crystallize into certainty. Pattern seeking is fundamental to human cognition. Our ancestors who saw patterns in animal tracks, weather signs, and seasonal changes survived better than those who didn't. But this same cognitive machinery malfunctions when applied to complex noisy systems. We see faces in clouds, hear messages in white noise, and find meaningful connections in random data. The geometry claims about ancient sites exemplify this. Connect enough dots, and patterns inevitably emerge, regardless of underlying meaning. Media history is full of examples where weak correlations metastasized into deterministic predictions. Solar maximum periods have repeatedly spawned doomsday prophecies. The Mayan calendar apocalypse of 2012, Y2K millennium bug catastrophism. Each cycle, new claims emerge that this time is different. This alignment is special. Public reactions range from curiosity to anxiety to outright panic. Vulnerable individuals make life decisions based on unfounded fears. Alternative media formats often omit crucial caveats. Documentary-style videos present speculation as established fact. Dramatic music, ominous narration, selective data presentation all create emotional responses stronger than rational evaluation. The phrase, "what they don't want you to know," implies conspiracy, suggesting mainstream science deliberately hides uncomfortable truths. This framing is seductive, but usually baseless. Contrast this with scientific culture. Science demands reproducibility. Claims must survive peer review, where experts scrutinize methodology, data quality, and logical soundness. Language is cautious, hedged with uncertainty. Papers include limitations sections acknowledging what wasn't measured or controlled. Conclusions are tentative, subject to revision with new evidence. This caution frustrates general audiences seeking definitive answers, but represents intellectual honesty. Content creators face a real tension. The power to spark curiosity comes with responsibility not to mislead. Speculation is valuable. Asking what-if questions drives discovery, but speculation must be labelled clearly. Presenting hypothetical mechanisms as proven facts crosses an ethical line. Audiences deserve to know where data ends and imagination begins. Here's an uncomfortable truth. Institutional neglect contributes to public distrust. When legitimate questions go unfunded and unexplored, people assume conspiracy rather than bureaucracy. If space weather and seismology communities simply dismissed solar tectonic coupling without investigation, their credibility suffers. Open questions demand open inquiry. Data gaps are opportunities for discovery, not excuses for silence. Open science practices help. Public data archives allow independent verification. Transparent methodologies enable replication. Citizen science projects invite participation. When institutions embrace these principles, trust increases. When data is hoarded, methods opaque, criticism dismissed, distrust grows. The scientific community shares responsibility for the public understanding of science. Psychological and sociological factors amplify these dynamics. We live in anxious times. Climate change, pandemics, geopolitical instability, economic uncertainty all create baseline stress. Cosmic-scale threats resonate because they're beyond individual control. Solar storms, asteroid impacts, supervolcanoes, these represent existential risks we can't mitigate personally. They symbolize our vulnerability in a chaotic universe. Solar-terrestrial coupling becomes more than a scientific question. It becomes a canvas for projecting deeper anxieties. Are we safe? Is nature predictable? Do unseen forces govern our fate? These questions transcend data and statistics. They touch on philosophy, meaning humanity's place in the cosmos. That's why debunking or confirming the hypothesis matters beyond immediate practical implications. Science, myth, fear, and hope intermingle in public understanding of natural disasters. Earthquakes have been attributed to divine wrath, underground demons, magnetic imbalances, and now solar storms. Each era explains disasters through its prevailing paradigm. Modern framing uses electromagnetic physics instead of angry gods, but the psychological need for explanation remains constant. Responsible communication navigates this carefully. Acknowledge uncertainty without dismissing questions. Present evidence fairly without cherry-picking. Distinguish speculation from conclusion. Respect audience intelligence while recognizing cognitive biases. It's a difficult balance, but essential for maintaining both scientific integrity and public engagement. While we wrestle with what we know and don't know about Earth's uncoupling, the broader cosmos continues its evolution. Discoveries in exoplanet science, galactic structure, and fundamental physics remind us that the universe still holds surprises. Let's step back and see what else recent research has revealed, placing our solar terrestrial mystery in a larger context. The Sun matters, absolutely, but it's one actor in an extraordinarily complex cosmic drama, an understanding that scale changes how we think about everything. Part 11. Exoplanet under fire. WASP 107b loses its atmosphere under stellar weather. Sometimes the best way to understand our own planet's relationship with its star is to look at someone else's disaster. 650 light-years away, a planet is dying. Not quickly, not dramatically, but steadily, inexorably, stripped bare by the very star that gave it light. The James Webb Space Telescope captured this planetary tragedy in unprecedented detail, and what it shows us matters for understanding Earth. WASP 107b is what astronomers call a hot Jupiter, though calling it hot sells the horror short. This gas giant orbits so close to its parent star that temperatures soar above 1000 degrees Celsius. But temperature is only part of the story. The real killer is the stellar wind, the constant barrage of charged particles that the star hurls into space. On Earth, we experience this as solar wind. On WASP 107b, it's a hurricane that never stops. The telescope detected something extraordinary. A massive helium cloud trailing behind the planet, stretching across space like a comet's tail. This isn't weather, this is atmospheric loss on a planetary scale. The star's ultraviolet radiation heats the upper atmosphere until gas molecules reach escape velocity. They leave the planet forever, streaming into space, never to return. The planet is bleeding its atmosphere into the void. Calculations suggest WASP 107b loses billions of kilograms of atmosphere every second. Over millions of years, this could strip away the entire gaseous envelope, leaving behind only a rocky core if one exists. The planet is being killed by its star, slowly but inevitably, through pure energetic bombardment. Why does this matter for our investigation? Because it demonstrates unambiguously that star-planet coupling is real, powerful, and capable of reshaping worlds. Not through metaphysical vibrations or mystical alignments, but through straightforward physics. Energy from a star reaches a planet. That energy has consequences. On WASP 107b, the consequence is atmospheric erosion. On Earth, could the consequence include geophysical effects? The physics differs in detail but shares fundamentals. Stars emit electromagnetic radiation across the spectrum, from radio waves through gamma rays. They emit particles, protons and electrons accelerated to high velocities. They generate magnetic fields that extend far into space, creating complex interaction zones when planets pass through them. All of this represents energy transfer from star to planet. The question is what that energy does when it arrives. For WASP 107b, the answer is straightforward. Ultraviolet photons hit atmospheric molecules, breaking chemical bonds, heating gas until it expands and escapes. The mechanism is well understood, mathematically describable, and directly observable. We can watch the planet losing its atmosphere in real time through spectroscopic analysis. Earth is more resilient. We orbit much farther from our star, receiving far less energy per unit area. We have a magnetic field that deflects most solar wind particles before they reach the atmosphere. Our atmosphere is denser, more gravitationally bound, harder to strip away. But the same physics applies. Solar energy reaches Earth. It interacts with our magnetosphere, ionosphere, and atmosphere. Under extreme conditions, effects can be dramatic. Consider this parallel. If a star can physically remove a planet's atmosphere through energetic coupling, is it really implausible that a star could influence crustal dynamics under certain conditions? The scales differ enormously. Atmospheric erosion involves low-mass gas molecules easily accelerated to escape velocity. Tectonic processes involve solid rock and enormous energies, but the principle of star-planet energy transfer is the same. Use an accessible metaphor. WASP 100b sits in the firing range of its parent star. Every second it takes hits. Each hit removes a tiny piece of the planet. Over geological time, those tiny pieces add up to planetary transformation. Earth sits farther from the firing line. Our star's shots are weaker, our defences stronger, but we still take hits. Space weather still impacts us. The question is whether those impacts extend deeper than we've traditionally assumed. The exoplanet example shows cosmic influence on planetary systems isn't fringe speculation. It's observed reality. Stars shape planets. They heat them, strip their atmospheres, drive their climate, and potentially influence their geology. The mechanisms vary, but the principle is universal. Planets exist within the energetic environment created by their stars. They're not isolated billiard balls floating in empty space. They're embedded in complex dynamic systems where energy flows constantly. While we debate earthquake triggers on Earth, exoplanet astronomers document atmospheric loss, tidal heating, orbital decay, and other stellar influences without controversy. These are accepted facts of planetary science. Perhaps the resistance to solar seismic coupling stems partly from historical accident, from disciplines developing in isolation, from questions falling between traditional fields where neither community felt responsible for investigation. WASP 107b will eventually lose its atmosphere completely if current trends continue. The planet will be fundamentally changed by its star's influence. Earth faces no such dramatic fate. Our sun is gentler, our distance safer, our defences adequate. But recognising that stars can reshape planets adds perspective. It reminds us that planetary systems are interconnected in ways still being discovered. This brings us to an even larger scale. Cosmic synchronization isn't limited to star and planet. Even galaxies separated by unimaginable distances sometimes move together in ways that surprise astronomers. Let's look at a recent discovery that challenges our understanding of how the universe organizes itself on the grandest scales. Part 12. A giant rotating filament of galaxies found by Meerkat. Cosmic synchrony on vast scales. The Meerkat radio telescope array in South Africa recently captured something that shouldn't exist, according to our simplest models of cosmic structure. A string of 14 galaxies stretching across hundreds of millions of light years, rotating together as a coherent structure. Not just moving in the same direction by chance, but actually rotating, spinning like beads on a cosmic string, synchronized across distances so vast that light takes hundreds of millions of years to traverse them. This discovery challenges intuitions about how the universe works at the larger scales. Galaxies should behave somewhat independently. They're influenced by dark matter, by gravitational interactions with neighbours, by the expansion of space itself. But on scales of hundreds of millions of light years, you'd expect chaos, randomness, individual galaxies doing their own thing. Instead, here's order, here's synchrony, here's a cosmic choreography that nobody predicted. The filament appears to be rotating as a single entity. The galaxies aren't just clustered together, they share coherent motion, spinning around a common axis. The rotation is slow by human standards, taking hundreds of millions of years for a single rotation. But on cosmic scales, the fact that it exists at all is remarkable. Something synchronized these galaxies. Something keeps them moving together despite the vast distances and complex dynamics involved. Astronomers suspect dark matter plays a role. Dark matter filaments form the cosmic web, the large-scale structure of the universe. Galaxies form where dark matter concentrates, along filaments and at intersection nodes. If a dark matter filament has angular momentum, rotates itself, then galaxies embedded in that filament might inherit that rotation. But confirming this requires detailed simulations and observations we're only beginning to gather. Why does this matter for our story? Because the universe demonstrates a love for synchrony, resonance, and emergent order even when the odds seem impossibly low. Systems separated by vast distances, connected by subtle forces, sometimes move together in ways that look coordinated. From planets locked in orbital resonances, to moons tidally synchronized with their primaries, to now entire galaxy filaments rotating coherently, nature creates patterns where you might expect only chaos. Draw an analogy carefully, because this isn't evidence for solar seismic coupling. Galaxies rotating together and solar storms triggering earthquakes are entirely different phenomena, but conceptually, both involve asking whether distant components of a system can influence each other in ways not immediately obvious. Both require us to think about connectivity, about how energy and information propagate through complex systems, about hidden harmonics that only reveal themselves under specific conditions. The universe is more interconnected than appearances suggest. Quantum entanglement links particles across arbitrary distances. Gravitational waves carry information about cosmic events across the universe at light speed. Magnetic fields thread through interstellar and intergalactic space, connecting regions separated by light years. Dark matter provides invisible scaffolding that shapes visible structure. Everywhere we look, connections exist where naive expectations would predict isolation. Our models of planetary and stellar systems are always incomplete. We understand the big effects, the dominant forces, the first-order approximations, but nature operates on all scales simultaneously. Tiny perturbations can matter if a system is near a critical point. Weak couplings can produce noticeable effects when amplified by resonance or accumulated over time. Second-order and third-order effects, usually negligible, occasionally become significant under special circumstances. The galaxy filament discovery reminds us to maintain humility. Astrophysicists didn't predict this structure. Nobody wrote papers anticipating coherent rotation on such vast scales. The universe surprised us. It revealed structure we weren't looking for and couldn't have easily predicted from first principles. That's normal in science. Nature is under no obligation to match our intuitions or conform to our simplest models. Astronomers responding to this discovery don't dismiss it as impossible or claim it violates known physics. They work to understand it, to refine models, to gather more data. They accept that the universe contains surprises and that science progresses by investigating anomalies. That's the attitude Earth scientists should adopt toward potential solar seismic coupling. Not blind acceptance, but genuine curiosity. Not dismissal without investigation, but skepticism paired with openness. Just as astronomers remain vigilant for surprises in cosmic structure, Earth scientists should remain open to unconventional but testable ideas about planetary processes. The data, the protocols must be rigorous, absolutely. The standards of evidence must be high, but closing the door prematurely, declaring questions off limits, refusing to collect data that might reveal surprising connections, that's anti-scientific. The cosmos operates on principles we're still discovering. From quantum scales to galactic scales, from femtoseconds to billions of years, nature demonstrates complexity that repeatedly exceeds our models. Why should we assume we've understood everything about how stars and planets interact? Why should solar-terrestrial coupling be the one area where surprises are impossible? But understanding requires good data, and collecting good data requires infrastructure. Infrastructure requires investment, coordination, and protection from degradation. Unfortunately, our ability to observe the cosmos, including our own star and its effects on Earth, faces growing threats. Let's examine how satellite proliferation is undermining our capacity to watch the skies. Part 13, Satellite Light Pollution and Observational Fragility. Why we must record space weather carefully. Thousands of new satellites are launching every year. Mega constellations for global internet coverage. Hundreds or thousands of satellites per network, multiplying the number of objects in low Earth orbit by orders of magnitude. This represents extraordinary technological achievement and potential benefit. It also represents an unprecedented threat to our ability to observe the universe. A 2025 study documented the problem comprehensively. Ground-based telescopes increasingly find their observations contaminated by satellite trails. Long-exposure astronomical images, once pristine, now show bright streaks where satellites crossed the field of view during exposure. Radio telescopes detect interference from satellite transmissions. The night sky, once dark except for stars and planets, now sparkles with artificial satellites visible to the naked eye. This matters for astronomy generally, obviously. Discovering distant galaxies, detecting faint exoplanets, searching for near-Earth asteroids, all become harder when satellites contaminate images. But it also matters specifically for space weather observation and solar monitoring. If our observational infrastructure degrades, our ability to track solar storms, measure their properties, and understand their effects diminishes proportionally. Solar observatories depend on clear views of the Sun, unobstructed by satellite interference. Chronographs imaging coronal mass ejections need clean data to track plasma structures. Magnetospheric satellites monitoring Earth's magnetic field environment require careful orbital management to avoid collisions. Ground-based magnetometers and radio receivers can be swamped by satellite transmissions, creating electromagnetic noise that obscures natural signals. Consider the forensic data checklist from earlier: high-quality magnetometer data, extremely low-frequency monitoring, ionospheric measurements, satellite observations of solar activity. All of these depend on observational infrastructure functioning properly. If satellites degrade that infrastructure through light pollution, radio interference, or increased collision risk forcing other satellites to maneuver constantly, the data quality suffers. Imagine a future scenario. A massive solar storm erupts, potentially one of the strongest in centuries. It races toward Earth. We need to track it, measure its properties, predict its impact. But our coronagraph observations are contaminated by satellite trails. Our magnetometers pick up interference from thousands of satellite transmissions. Our ionospheric measurements are confused by satellite-induced disturbances. We still detect the storm, but our understanding is compromised. We can't build the complete forensic dataset needed to test hypotheses about electromagnetic coupling to seismic systems. The risk extends beyond this specific question. Space weather affects power grids, satellites, communication systems, aviation, GPS, basically every technological system modern civilization depends on. Accurate space weather forecasting requires robust observational networks. Degrading those networks through satellite proliferation is short-sighted. We're trading long-term observational capability for short-term commercial advantage. Advocacy for better protections becomes essential. International coordination on satellite brightness, reducing reflectivity to minimize interference with ground-based astronomy. Careful frequency management, avoiding radio bands crucial for scientific observation. Orbital planning that preserves crucial observation zones. Collision avoidance systems that don't require constant maneuvering, degrading measurement stability. These protections are technically feasible, but require regulatory will. The larger ecosystem includes space weather monitoring in orbit and on the ground. Solar observatories at the L1 Lagrange point between Earth and Sun. Magnetospheric satellites in various orbits measuring particle populations and magnetic fields. Ground-based magnetometer networks. Radio receivers tracking ionospheric disturbances. All of this forms an integrated system for understanding space weather. Degrade any component, and the system's effectiveness suffers. Space weather impacts extend beyond technology. If electromagnetic coupling to seismic systems proves real, space weather becomes a geological hazard too. That makes robust monitoring even more critical. We need to detect, characterize, and track solar storms with high precision. We need long-term archives for statistical studies. We need coordinated international networks sharing data openly. All of this requires infrastructure that satellite proliferation threatens. Reflect on human short-sightedness. We're excellent at seeing immediate benefits and terrible at anticipating long-term costs. Satellite internet provides connectivity to underserved regions, a genuine good. But we're deploying it without adequately considering impacts on scientific observation, space debris, collision cascades, or degradation of humanity's ability to watch the cosmos. Future generations may curse our recklessness. The solution isn't halting satellite deployment. Technology provides enormous benefits. The solution is thoughtful regulation balancing multiple priorities. We can have satellite internet and dark skies. We can have global connectivity and preserved observational capability. It requires planning, coordination, and willingness to accept constraints on unfettered commercial expansion. Whether we collectively possess that wisdom remains uncertain. Data and observation form the foundation of understanding. Without good data, science stalls. Theories remain untested. Questions remain unanswered. If we want to resolve mysteries like potential solar seismic coupling, we need to maintain and improve our observational infrastructure. That means protecting it from degradation, whether from satellite proliferation, funding cuts, or institutional neglect. But observation isn't the only field evolving rapidly. Fundamental physics gets reframed as instruments improve. Phenomena once thought impossible become routine as detector sensitivity increases. Let's look at gravitational wave astronomy, where better instruments reshaped our understanding of the universe in less than a decade. Part 14, Gravitational Wave Archive, LIGO, Virgo, CAGRA, O4 Run, and Puzzling Black Hole Events. How better instruments reshape understanding fast. Before September 14th, 2015, gravitational waves existed only in theory. Einstein predicted them a century earlier as ripples in space-time caused by accelerating masses. But detecting them seemed impossible. The effects are tiny, stretching and compressing space by fractions of a proton diameter across kilometres. Building instruments sensitive enough required technological advances spanning decades. Then LIGO detected its first gravitational wave. 2 black holes, each roughly 30 solar masses, spiraled together and merged. The collision released more energy in gravitational waves than all the stars in the observable universe emit as light during the same instant. That energy rippled across space, eventually reaching Earth, causing LIGO's mirrors to shift by impossibly small amounts. But shift they did, and we detected it. The detection marked one of those rare moments in science when everything changes instantly. Physicists had spent careers building instruments most people thought would never work. Skeptics argued the signals would be too weak, the noise too overwhelming, the technical challenges insurmountable. Then came that first detection, unmistakable in the data. 2 detectors, thousands of kilometres apart, recorded the same signal within milliseconds. The waveform matched theoretical predictions with eerie precision. The universe had spoken, and we'd finally learned to listen. Since then, gravitational wave astronomy has exploded. The 04 observational run, which began in 2023 and extended through 2025, detected dozens of new events. Black hole mergers, neutron-star mergers, possibly exotic objects we don't yet understand. Each detection adds to our catalogue of cosmic collisions, refining our understanding of stellar evolution, black hole populations and cosmic history. The catalogue grows steadily. Every few weeks during observing runs, another detection, another pair of black holes merging somewhere in the universe, another neutron-star collision broadcasting its death spiral across billions of light years. The detections have become almost routine, which itself represents revolutionary progress. What was impossible before 2015 now happens regularly enough that astronomers can study populations, identify trends, and test models statistically. Some 04 events puzzled astronomers immediately. Black holes with unexpected masses, neither light enough to form easily from stellar collapse nor heavy enough to be supermassive. These intermediate mass black holes occupy a strange zone where formation mechanisms remain unclear. Standard stellar evolution doesn't naturally produce them. They're too massive to form from individual star collapse, but too light to be the supermassive giants lurking in galaxy centres. Black holes with unusual spins appeared in the data as well. Spin carries information about formation history. A black hole formed from a single collapsing star should spin in a direction related to the star's original rotation. But some detected black holes spin at odd angles relative to their orbital motion, suggesting formation through multiple mergers or captures, rather than simple stellar collapse. Each unusual spin orientation forces theorists to reconsider how black holes form and evolve. Potential neutron star and black hole mergers showed up with properties challenging existing models. These hybrid mergers are rare and valuable because they probe physics at extremes. Neutron stars represent matter compressed to nuclear densities. When one merges with a black hole, we get information about both exotic objects simultaneously. But some detections showed mass ratios or merger signatures that didn't quite match predictions, indicating our models still miss important physics. Each anomaly forces theorists back to their calculations, questioning assumptions, refining models. This is science working as intended. Theory makes predictions. Observations test those predictions. When observations disagree, theory adapts. The process iterates, each cycle bringing understanding closer to reality. Nobody declares the anomalies impossible or dismisses them as instrumental artifacts. The community takes them seriously, works to explain them, and accepts that our understanding remains incomplete. This exemplifies how better instruments drive science forward. Before LIGO, we knew black hole mergers should occur but had never observed one. Theories existed but lacked empirical grounding. Astrophysicists could calculate what should happen when black holes merge, predict the gravitational waves they'd emit, estimate merger rates. But without observations, these remained educated guesses. Within years of first detection, we've observed enough events to test theories, rule out some models, refine others, and discover unexpected phenomena nobody predicted. The transformation happened quickly by scientific standards, a decade from first detection to mature field with dozens of events catalogued and analysed. That speed reflects both the quality of the instruments and the readiness of the scientific community. When LIGO detected its first gravitational wave, teams were prepared to analyse data, interpret results, and publish findings rapidly. The infrastructure existed intellectually and institutionally to exploit the breakthrough immediately. Gravitational wave astronomy parallels other fields where improved instrumentation revolutionised understanding. Radio astronomy revealed cosmic structures invisible to optical telescopes. When Grota Robert built the first radio telescope in his backyard in the 1930s, he opened a new window on the universe. Radio galaxies, quasars, pulsars, the cosmic microwave background, all became visible through radio eyes. Each discovery reshaped astronomy. Space telescopes observing ultraviolet and X-ray light discovered high-energy phenomena missed from the ground. Earth's atmosphere blocks these wavelengths, rendering ground-based observations impossible. Only by launching telescopes into space could we see the hot, violent universe. Supernova remnants, accretion disks around black holes, active galactic nuclei powered by supermassive black holes consuming matter. Each new wavelength revealed phenomena previously invisible and often unexpected. Neutrino detectors opened windows on the Sun's interior and supernovae. Neutrinos interact so weakly with matter that they pass through the Sun and Earth almost unimpeded. This makes them extraordinarily difficult to detect but incredibly valuable. They carry information directly from nuclear reactions in stellar cores. Detecting solar neutrinos confirmed our models of solar fusion. Detecting neutrinos from supernova 1987A provided the first direct observation of core collapse, validating decades of theoretical work. Each new type of observation, each improvement in sensitivity, reveals surprises. The pattern repeats across astronomy's history. Build better instruments, look more carefully, and nature shows you things you didn't expect. Sometimes the surprises are minor, refinements of existing knowledge. Sometimes they're revolutionary, forcing complete reconceptualization of phenomena. Draw the parallel to our central question. Long-held assumptions about black hole formation are being challenged by new data. Nobody dismisses these challenges as impossible. Astronomers embrace them, working to understand what the data means. The intermediate mass black holes, the unusual spins, the unexpected merger rates, all get treated as genuine puzzles worth solving. Funding agencies support research investigating these anomalies. Journals publish papers proposing explanations. Conferences feature talks debating interpretations. Similarly, assumptions about solar storms and Earth being unconnected systems may need re-examination if better data emerges. The key phrase is if better data emerges. Gravitational wave detection succeeded because instruments existed, operated reliably, and collected high-quality data. Seismoelectromagnetics hasn't reached that stage yet. The monitoring networks are sparse, data quality variable, coordination limited. But the methodological lesson from gravitational waves applies directly. For gravitational waves, we move from 0 detections to dozens by building better detectors. The instruments improved gradually over decades. Engineers solved technical challenges one at a time. Vibration isolation systems protected mirrors from seismic noise. Laser stabilization achieved unprecedented frequency stability. Vacuum systems maintained ultra-high vacuum over kilometers of beam pipes. Sensitivity increased with each upgrade cycle. Noise sources got identified systematically and eliminated or mitigated. Global coordination allowed multiple detectors to observe simultaneously, confirming detections and localizing sources. LIGO operates 2 detectors in the United States, separated by thousands of kilometers. Virgo operates in Italy. CAGRA operates in Japan. When multiple detectors see the same signal, false positives become vanishingly unlikely. Time delays between detections at different sites allow triangulation, narrowing the source's sky position. This global network transforms gravitational wave astronomy from novelty to precision science. The result was revolutionary science achieved through methodical instrument development and international collaboration. No single breakthrough made it possible. Decades of incremental improvements accumulated until detection became feasible. Then continued improvements transformed feasibility into routine capability. Could something similar happen for seismoelectromagnetics? If we invested in comprehensive monitoring networks, if we coordinated observations globally, If we maintained long-term archives and applied sophisticated analysis techniques, could we move from ambiguous case studies to conclusive evidence? Maybe. The physics differs enormously from gravitational waves. The signals are different, the noise sources are different, the challenges are different. But the methodological lesson applies universally. Better instruments, better data, better analysis. These can transform marginal questions into resolved science. What specifically changed for gravitational waves? Improved sensitivity meant detecting weaker signals from farther away. Early predictions suggested LIGO might detect a few events per year. Enhanced sensitivity pushed detection rates higher, revealing that compact binary mergers occur more frequently than some models predicted. Better signal processing extracted faint signals from noise. Sophisticated algorithms distinguish gravitational wave signals from instrumental artifacts and seismic noise. Machine learning techniques now help identify candidate events in real time. Global coordination provided independent confirmation and better sky localization. Multiple detectors seeing the same event dramatically reduces false positive rates. Triangulation from time delays improves angular resolution. Multi-messenger astronomy, combining gravitational waves with electromagnetic observations, added context. The neutron star merger detected in 2017 produced gravitational waves observed by LIGO and Virgo, plus gamma rays, X-rays, optical light, and radio waves detected by telescopes worldwide. This multi-messenger observation confirmed that neutron star mergers produce heavy elements and short gamma-ray bursts, resolving long-standing questions. Sustained funding and international collaboration maintained operations and improvements. Gravitational wave astronomy required decades of investment with no guarantee of success. Funding agencies, primarily in the United States initially but expanding internationally, supported the work through technical development, construction, and operations. When detection succeeded, the investment was vindicated, leading to continued and expanded support. Similar elements could advance seismo-electromagnetics if adopted. Improved sensor networks with better time synchronization. Deploy magnetometers, extremely low-frequency receivers, and seismometers globally with GPS-disciplined clocks ensuring microsecond timing accuracy. Sophisticated signal processing distinguishing genuine geophysical phenomena from noise. Machine learning algorithms trained on large datasets could identify patterns humans miss. Multi-instrument observations combining seismology, electromagnetics, ionospheric physics, and space weather. No single measurement type suffices. Correlation across multiple independent observables strengthens conclusions. Open data sharing enabling independent analysis. Gravitational wave data is publicly archived, allowing researchers worldwide to analyze it independently. This transparency builds confidence and accelerates discovery. Sustained funding supporting long-term monitoring. Short-term projects can't answer questions requiring decades of observations. Institutional commitment to long-duration monitoring programs is essential. Reassure the audience that this doesn't mean solar seismic coupling is as solid as gravitational wave detection. Gravitational waves are now established science, repeatedly observed, theoretically understood, and fully accepted. Einstein predicted them. Theoretical work spanning a century developed detailed models. Observations confirmed predictions with stunning precision. The science is settled. Solar seismic coupling remains speculative, with weak evidence and no consensus mechanism. Most researchers remain skeptical. Statistical correlations are ambiguous at best. Physical mechanisms are poorly constrained. No smoking gun observation exists. The two situations differ dramatically in evidential support. But the trajectory from speculation to acceptance requires exactly the elements gravitational wave astronomy demonstrated. Better instruments, better data, sustained investigation. The lesson is methodological, not evidential. Science advances when it takes questions seriously, invests in proper investigation, and lets data drive conclusions. Dismissing questions without adequate investigation doesn't advance knowledge. Neither does accepting claims without sufficient evidence. The path forward requires building infrastructure, collecting data, testing hypotheses rigorously, and accepting whatever conclusions the evidence supports. That process works regardless of the field or the specific question. Gravitational wave astronomy transformed from marginal pursuit to mainstream physics in under a decade because the instruments existed, the observations succeeded, and the community responded appropriately. Funding continued. Papers got published. Careers developed around the field. Institutions created gravitational wave research groups. Universities hired faculty specializing in the area. The scientific ecosystem embraced the new field because evidence compelled acceptance. Whether solar seismic coupling follows a similar trajectory depends on whether we collectively decide the question merits serious investigation. The physics might prove it negligible. Detailed studies might show effects too small to matter practically. But we won't know until we look properly. We can't dismiss the question based on intuition or preliminary studies using inadequate instruments. We need to build the proper tools, collect the proper data, and let evidence decide. We stand at such a crossroads now. New data becoming available, new technology enabling observations previously impossible, new openness to interdisciplinary questions. The question is whether we'll seize this opportunity or let it pass. Gravitational wave pioneers seized their moment, persisting through decades of skepticism and technical challenges. Their persistence transformed physics. Perhaps seismo-electromagnetics deserves similar commitment. Perhaps not. But making that decision requires honestly assessing what's known, what's possible, and what's at stake. What should we actually do now? And why does this investigation matter beyond academic curiosity? Part 15. Big reflection and final takeaways. What we should do now and why this matters. We've travelled from a moment of apparent synchronization, solar explosion, and terrestrial rupture occurring simultaneously, through mechanism speculation, statistical ambiguity, anomalous features, and finally into broader cosmic context. Now we need to synthesize what this journey reveals and chart a path forward. What have we learned? What don't we know? What should happen next? Recap the journey honestly. We started with 3 documented facts: a powerful M8.1 solar flare, an Earth-directed coronal mass ejection, a magnitude 7.0 earthquake in Alaska, and reports of electromagnetic anomalies detected around the same time. These facts don't by themselves prove causation. They establish correlation, raise questions, and demand investigation. We explored proposed mechanisms: electromagnetic coupling through telluric currents, piezoelectric effects in crustal rock, ionospheric disturbances propagating to the ground. The physics isn't impossible, but scaling from known effects to earthquake triggering involves enormous uncertainties. Energy budgets seem wrong by orders of magnitude unless special circumstances create threshold effects where small perturbations matter. We examined statistical studies attempting to correlate solar activity with seismic rates over decades. Results are contradictory, methodologies disputed, and consensus skeptical. Pattern-seeking selection bias and multiple comparison problems plague this research area. Weak correlations that appear in some datasets disappear in others. No robust, reproducible relationship has been established despite decades of effort. We looked at anomalies making this specific event unusual: the double explosion coronal mass ejection morphology, precursor seismic quietness, and speculative geometric relationships to ancient sites. Each anomaly is intriguing but not uniquely diagnostic. Alternative explanations exist. None constitute proof of solar triggering. We broadened perspective through cosmic context. Exoplanets losing atmospheres to stellar bombardment demonstrate star-planet coupling at extreme scales. Galaxy filaments rotating coherently show the universe creates synchronized structures across unimaginable distances. Gravitational wave detections prove that better instruments can rapidly transform speculative questions into established science. Each example reminds us that nature contains surprises and that maintaining curiosity serves science better than premature dismissal. Distill the core message carefully. We don't know yet whether solar storms can trigger earthquakes through electromagnetic coupling. The possibility can't be dismissed out of hand based on current evidence, but it also can't be accepted without much stronger data than currently exists. This is genuinely uncertain territory, uncomfortable for people seeking definitive answers, but honest about the state of knowledge. Ignoring this question entirely would be irresponsible if there's any chance the coupling is real. Earthquakes kill people, destroy infrastructure, and cause suffering. Space weather disrupts technology we depend on. If these hazards are coupled, even weakly, that changes risk assessment and preparedness planning. We can't afford to ignore potential hazards just because they cross disciplinary boundaries or seem initially implausible. Provide concrete recommendations for multiple audiences. For scientists, build or expand global time-synchronized monitoring networks. Deploy magnetometers, extremely low-frequency sensors, and seismometers with rigorous calibration and metadata. Archive raw data openly, enabling independent analysis and replication. For institutions, fund interdisciplinary research combining space weather and geophysics. Create seed grants supporting exploratory studies. Encourage collaboration across traditional boundaries. For citizen scientists, participate in distributed monitoring efforts. Build or deploy sensors contributing to community networks. Pressure institutions to release archived data currently sitting unused. Engage with open science practices making research accessible beyond academic paywalls. For the general public, stay informed without panicking. Demand transparency from researchers and media. Learn to distinguish speculation from conclusion, correlation from causation, possibility from certainty. Offer a balanced speculative scenario framing the stakes. Imagine a future where a gigantic solar storm, stronger than any in recorded history, slams into Earth. Simultaneously, a major fault system stressed near failure responds to the electromagnetic disturbance. A magnitude 8 earthquake strikes a populated region. Infrastructure fails from both space weather and seismic damage simultaneously. Emergency response systems, already strained by the earthquake, face additional challenges from communication failures and power grid collapse caused by the geomagnetic storm. Is this plausible? Maybe. Is it certain? Absolutely not. But it's not science fiction. Both components, severe space weather and major earthquakes, occur independently. If they're coupled, even weakly, correlated occurrence becomes possible. And if observational infrastructure has degraded due to satellite proliferation or funding cuts, we might not even see it coming clearly. That combination of hazards, infrastructure vulnerability, and observational blindness represents a plausible worst-case scenario worth considering. Acknowledge the ghost in the machine. Even if catastrophic coupling proves negligible or non-existent, research in this area yields benefits. Better understanding of Earth's electromagnetic environment improves geophysical models. Enhanced space weather monitoring protects technology. Improved seismic networks advance earthquake science. Cross-disciplinary collaboration sparks innovation. Open data practices accelerate discovery. The investigation itself has value regardless of whether the specific hypothesis proves correct. Close on a philosophical note, Earth is not isolated. Our planet exists within the Sun's electromagnetic environment, bathed constantly in solar wind, buffeted by storms, responding to our star's moods in ways we're still discovering. We've always known the Sun gives us light and warmth, drives our weather, and powers life through photosynthesis. But the relationship may be deeper than we thought. Perhaps not through magic or mysticism, but through physics we barely understand. Through subtle couplings operating on scales where current instruments struggle to measure. Through threshold effects that matter only under rare alignments of circumstances. Through connections we haven't mapped because we weren't looking in the right places with the right tools. Our star is alive in the sense that it's dynamic, changing, actively influencing its surroundings. It generates magnetic fields spanning the solar system. It hurls plasma into space. It varies in output over multiple timescales. We orbit within this active environment, protected but not isolated, influenced but not controlled. Understanding that relationship fully requires humility, acknowledging how much we don't know. Science progresses through cycles of certainty and uncertainty. We build models explaining observations. The models work until they don't. Anomalies appear. New data challenges old assumptions. We refine or replace models. Understanding deepens. This is normal, healthy, how knowledge advances. Treating any model as final truth guarantees eventual surprise. Final call to action for viewers. Stay informed, but think critically. Demand data, but understand uncertainty. Watch the skies. Not for apocalyptic signs or alien visitors, but for subtle whispers of connections we're only beginning to grasp. Support science that asks difficult questions, even when answers remain elusive. Pressure institutions to maintain observational infrastructure and share data openly. The sun will continue erupting. The earth will continue shaking. Whether those processes are connected in ways we don't yet understand remains an open question. Answering it requires better data, sustained investigation, and intellectual honesty. We might discover genuine coupling, expanding our understanding of planetary hazards. We might discover the effects are negligible, reinforcing traditional models. Either way, we'll know more than we do now. That's the fundamental goal of science: to know more, to understand better, to replace speculation with evidence, uncertainty with knowledge, fear with comprehension. This investigation exemplifies that goal. We started with a mystery, a coincidence too precise to ignore. We've examined it from multiple angles, acknowledging uncertainty while exploring possibilities. Where it leads depends on whether we collectively decide the question matters enough to answer properly. Earth and Sun locked in gravitational, embrace for over 4.5 billion years, partners in a cosmic dance older than life itself. We've studied this relationship since astronomy began, learning constantly, discovering repeatedly that simple descriptions never capture full complexity. Maybe we've understood the basics, maybe mysteries remain. Either way, the relationship continues, dynamic and real, worthy of our attention and our best efforts to comprehend it fully. The sun rises tomorrow, as it has for eons. The ground beneath our feet may tremble, as it has throughout geological time. Whether these events connect in ways current science struggles to explain remains uncertain. But uncertainty is not ignorance. It's the boundary where knowledge meets mystery, where investigation begins, where discovery becomes possible. That's where we stand now, looking at data, asking questions, building tools, and wondering what the universe will reveal next.